Good day all, and welcome to Lab 3. We're going to start off with Investigation 1 in just a moment, but here's a little summary of what we're going to be working on. Lab 3 ties the idea, first of all, it develops a method for measuring forces reliably. You're also going to learn how to use a force probe or force sensor to measure force. We're going to explore how the motion of an object is related to the forces applied to it. And we're going to see if there's a mathematical relationship between the force applied to an object and its acceleration. Now, in the previous lab, we've used a motion detector in order to display position time, velocity time, and acceleration time graphs. We didn't care how to get it moving. We just wanted to get them moving to make the measurements and show the relationships between those properties. But now we have to ask the question, what is the effect of force? We used the fan cart, for example, to apply a force to the cart to get it to accelerate. So is there a relationship between acceleration and force? In order to do that, we must first be able to measure force. And so that's where Investigation 1 comes into play, measuring forces. And as you can see right now, we've got it set up. I have a rigid rod, which is in a rod stand here, and I'm going to need it as a base. And I've got a taped distance. Using this stick right here, we see that the tape distance is just about 15 centimeters. And we also have a number of rubber bands, which I have located right here. Excuse me. So what we're going to do is we're going to answer some questions here involving how hard is a pull, how large is a pull, how we can measure pulls. So let's start off. Let's take a rubber band. And this is, I will admit, this is where it's going to be a little difficult because we have to use the kinesthetic sense, that is to say, your muscle sense. So what we're going to do here, and I'll try to give you some kind of verbal feedback on all of this, is we're going to take a rubber band. We attach it so that it's fixed in position on that rod. And I'm going to pull it a specific length. And this length, in this case, is 15 centimeters. So I take the rubber band and I pull it out. And I'm going to feel that it has some kind of force. It feels like that the rubber band is pulling back against me. Okay. Now the length we've chosen is 15 centimeters, so you write that down on page 64. And now that I've pulled this out and had some kind of feeling on how much the rubber band is pulling back, the next question is what happens if I take a second rubber band, place it on, and pull it out. And when I pull it, I feel like I've got to pull harder. Now, how much harder is hard to quantify? If I pull one, I have a certain amount of feel to it. If I pull two, the other one, it has about the same amount of feel. But if I pull both of them at the same time, I've definitely got to pull stronger. 2 times, maybe 3 times, even more. It's hard to quantify. I definitely do have to pull harder. So question 1-1, how does the combined force of 2 rubber bands compared to what I felt when only 1 rubber band was used? And it felt like it was definitely stronger. How much time? How much? Hard to tell. Now, if we use 3 rubber bands, then when I grab hold of it and pull it, and I'm trying to grab all 3 of the rubber bands at the same time, when I pull it, it's definitely harder. I'll go ahead and go to 4 rubber bands and see how that feels. And I will pull it out, and I'm straining very hard to try to pull that. It's definitely much harder to do. And then here's my 5th rubber band. And I'll grab that and I'll pull it out. And as you can see, I don't know if you can see it or not, but I'm definitely straining, trying to hold it in place. Excuse me. I'm definitely straining, trying to hold it in place. Now, a good example about how strong rubber bands are is you could do a YouTube search and come up with a rubber bands and watermelons. In fact, let me go ahead and transition over there and see if I can find it. So anyhow, what that is a little warped way of looking at it, but as you can see, the more rubber bands you add, the greater the force, and in the case of that watermelon, the more rubber bands we put on, the harder the force, and eventually there was enough force to cause the watermelon to explode. Let's go ahead and go back to the questions, page 65. Suppose you stretched a rubber band your standard length by pulling on it. Now you want to create a force that's 6 times as large. How could you create such a force? Well, as I said before, when I pulled with one rubber band, it felt like it had some kind of force pulling back. When I pulled with 2 rubber bands, it almost seemed like it was double the force, and so on up the line. So when I got up to, so if I want to make 6 times the force, then it would make sense for me to add 6 rubber bands altogether in pulling them out that standard distance. Question 1-3, suppose you applied a force with a stretched rubber band one day, and several days later you wanted to feel the same force or apply it to something. How could you assume that the forces were the same? Well, we would have to make sure of a couple things. First, that the distance was the same, that we were pulling our rubber band. Second, we would have to assume that our rubber band was still the same, and that our rubber bands were still identical. If I use different rubber bands, I'm going to get a different force pulling on it. And then, of course, if we try to get the same laboratory conditions, because I don't know what effect temperature or humidity would have on it. Now that leads to question 1-4. Do side-by-side rubber bands provide a convenient way of accurately reproducing forces of many different types, or many different sizes, And the answer is yes. If I pulled with one rubber band, I would get a certain amount of force. If I pulled with 2 rubber bands, it seems like I would get twice as much force. If I pulled with 3 rubber bands, I would get 3 times as much force. And so I could use a standard unit of measure. That unit is how much force required to pull a rubber band a specific distance. So yes, I could create my own standard of measure. So this would be 1 rubber band of force, then this would be 2 rubber bands of force, and so on up the line. Of course, the real test is whether or not we can do this, if we can get some accurate measurements for that. And for that, we're going to go ahead and bring up a graph and do some measurements in activity 1-2. So now I've got it set up to do activity 1-2. And what we're going to use to measure the force is this device right here. It's a high-resolution force sensor. And what I'm going to do is I'm going to grab the rubber band with the hook and then pull it out to the known distance and measure the force. Now, because this is an very sensitive electronic device, what I have to do in between each trial is I've got to push this button here called 0. It's just like if you're doing your calibration of a scale. You press the 0 button to make sure that all the stray voltage is gone so that it's actually reading a 0 load. So we've got it plugged in. That's step number 1. Step number 2, we 0 the force sensor. Okay. Then step number 3, attach one end of the rubber band to something that can't move as we've got it before. Then we're going to pull horizontally. So I'm going to go ahead and grab hold of a rubber band. And I'm going to hook it here. Again, 0 the force sensor. Pull it out the fixed distance, in this case 15 centimeters. And I'm going to start recording for about 3 or 4 seconds. And we'll stop right there. So there's our scale there. And as you can see, it's a fairly straight line. We'll go ahead and expand the time scale. All right, so what is the force? The force to pull one rubber band out that distance, because it's a straight line, I'll go ahead and find the mean. And so the mean happens to be 1.15 units. I've chosen some arbitrary units here for force. And you'll see where it goes from here. But for right now, we're going to call this 1.15 units. Okay. Next, we go to page 66, step number 4. We could continue to do this. But instead, we're going to use a different method, which is called a sampling method. And in a sampling method, I'm not going to record every bit of data. I'm only going to take a sample of a bit of data and let the computer graph for me. So let me go ahead. I'm going to reconfigure at this moment, and you'll see what I'm talking about. All right. In this mode, what we're going to do is we're going to pull the rubber band out to a certain position, and then at the bottom where it says keep sample, we will click on it. So we'll be able to get a scale. Well, let me show you. So we've got step number 4 set up. Step number 5, record your force probe readings for each number of rubber bands on the table below. So first we're going to zero the force sensor. Then we're going to start recording. Now, as you can see when I have on preview, we are recording, but the data is not being recorded. So I'm going to have a table set up so you can write down the data on page 66. So as you can see right now, with 0 force, we have 0 rubber bands hooked on. We're going to have 0 force. So there's, again, 0 rubber bands hooked on. We have 0 force. So let's pull it out. 1 rubber band out 1 standard distance, 15 centimeters. Okay. The data holds in place. Right now it's at 1.2. We're going to hold it in place. We go to keep sample, and it's going to record that piece of information. Let me go ahead and turn off that, and let's move on. Now we'll hook on a second rubber band and pull it out that fixed distance again. Wait for the data to stop, to settle down. It looks like it's settling around 6.0, 5.9. Let me pull it out a little further. When it settles in place, I click on Keep Sample. Now we're going to go and hook up a third rubber band. And now I'm going to hook up a fourth rubber band. I don't know if you can see, but I am definitely struggling to keep the rubber band in place. And then a fifth rubber band. I'll hook up, pull it out, hold it in position, click Keep Sample, hit Stop, and now I've got my data set. So 1 rubber band is a force of 1.17 units. 2 rubber bands is a force of 2.58 units. 3 rubber bands is 3.97 units. 4 rubber bands is 5.26 units. Oh, I'm sorry. 4 rubber bands is 5.26 units, and 5 rubber bands is 6.39 units. Let me rescale the graph so you can see it a little better. It looks like, now the question becomes, is this a linear or a proportional? Look at the comment on page 66. We're interested in the nature of the mathematical relationship between the reading of the force probe and the force in rubber band units. This can be determined from the graph by drawing a smooth curve that fits the plotted data points. Some definitions of possible mathematical relationships are shown below. It has a little bit of curve, but really not that much. That's a little variation there, so we can throw out that it's a general function. In fact, it's probably a more specific function. If it is a linear function, then it's going to make a straight line, but the y-intercept is going to be something other than 0. Well, we've already seen that if I have 0 force, if I have 0 rubber bands on it, we had 0 force. And so our initial point is going to be 0. That means y is proportional to x. And so we're going to use the fit routine for a proportional equation. I'll click on the pull down, and proportional is the very first one. I'll click on that, and there's your proportional line, where A is the slope, A times the index. So A is the slope of 1.3, and that makes sense. It seemed like every time I added a plus or minus 0.13, it seemed like every time I added another rubber band, I added about 0.13. So we had a 0.12 gain from 0 to 1. We had a 0.14 gain from 1 to 2. We had a 0.14 gain from 2 to 3. We had a 0.13 gain from 3 to 4, and just more like a 0.12 gain from 4 to 5. All right, so it's not very specific, but it looks like a pretty good fit. So go ahead and stop it this point and go ahead and sketch the graph on the top of page 67. Now, question 1-5. How are force probe readings related to the size of the pull exerted by the force probe hook on the rubber band? So describe the mathematical relationship in words, and it looks like that as I increased the number of rubber bands, the amount of force required to pull it had to increase. It is a proportional. Based on your graph, this is question 1-6. What force probe reading corresponds to the pull of one rubber band when stretched to your standard length? And averaging that all out, it would be the slope of that line, which would be about 1.3. So, one rubber band pulled out would give a force of about 1.3 units. Since each of these rubber bands are going to be slightly different, there's going to be some variance, and that's why the plus or minus 0.13. But it's close enough for our purposes. All right, so in the comment, you can use your measurements to define a quantitative force scale. You might call that the rubber band scale, or give yours or your partner's name. Whenever the force probe has the reading corresponding to the pull of one rubber band stretched to the standard length, the force is equivalent to one rubber band. Any larger force can be measured as some number of these units. Your graph relates two ways of measuring force. One with the standard stretches of different numbers of rubber bands, which would be rubber band units, and the other with a force probe. Such a graph is called a calibration curve and is used to compare measurements of quantities made with two different measuring instruments. You could use it to convert forces measured in force probe units to rubber band units and vice versa. What I'm trying to say is this, that we now have a scale. One rubber band unit, two rubber band units, three rubber band units, and so on down the line. So if I take my force sensor and I pull on it, then I should be able to measure the force in these force units. So I can calibrate it that way. I'm not going to. What we're going to use for our standard unit is going to be the Newton. And I'll explain on next week what the magnitude of a Newton is. So let's go ahead and take a look at activity 1-4, and I'll go ahead and calibrate a force sensor. So here is this right here is a force sensor of 0 to 5 newtons. This is a spring scale. And what I'm going to do is I'm going to use the force sensor here, which is calibrated in units of applied force of rubber band units, fraction rubber band units, and I'm going to compare it to this spring scale. Let's see if we can still get that same kind of effect. So let me go ahead and, first of all, I'm going to reposition the camera. So please pardon while there's a little bit of a stretch there. Okay. And I'm going to hook this end to the rod so that it doesn't move as well. All right, now I'm going to go ahead and calibrate our force sensor to the spring scale. So, first thing we're going to do is we're going to zero the force sensor. Here's a couple of changes. First of all, the graph I've changed. So we have applied force on the y-axis, but this time it's the spring scale reading on the x-axis. I've already entered the numbers I want to compare against. 1 Newton, 2 Newtons, 3 Newtons, 4 Newtons, and 5 Newtons. So when I do the comparison, I will pull out the force, I'll use the force sensor, hook it up, pull this out so that it reads 1 Newton, and then we'll keep the sample there. So it's going to take a little bit of coordination here. So we'll start off recording. Zero the force sensor. We'll start recording. We should have 0, 0, so let me go ahead and pull this up real quick. Yep, there's the 0 point. You can see that it's not recording there. And now I will pull this out, and there's 1 Newton of force that I'm reading, and we seem to have an error here because my force sensor is only reading 32. The reason why is the spring scale is being held in place by the ground. So let me pull it up a bit. There we go. That's holding it in place. Oh, I'm sorry. That's right. So we'll hold that in place there. We'll go ahead and keep sample. I'm going to pull it out to 2 newtons. and keep sample there. Here's 3 newtons. Here's 4 newtons. And all the way out to the end at 5 newtons. And we'll go ahead and hit the stop. And as you can see, we have another linear relationship. And in fact, if we extended it out, we could extend this out all the way to 0, 0. And so we can get a unit conversion here. If I go ahead and do the linear fit, or not the linear fit, but the proportional fit, that's not showing proportion, so let's go ahead and go straight to linear. There we go. On our linear fit, there we go. On our linear fit, we see that if I pull out 1 Newton of force on the spring scale, it's going to pull out 0.337 arbitrary units on the force scale, on the force sensor. What that means, if you recall, 1 rubber band unit was about 1.1 of these arbitrary units. So it turns out that about 4 newtons of force is required to get about 1 rubber band unit, and we can check that. 1 rubber band unit is about 1.2 arbitrary units. That gets us to about 3.5 newtons. Okay, so question 1-8. Do your force probe readings correspond to your spring scale readings? The answer is yes, because as you can see, there is a linear relationship. And we could probably apply a correction to the applied force. And if we applied a correction to the applied force, we could probably rescale this into newtons. And so I'm going to go ahead and do that. And I'll just pull out my calculator. And instead of force, I'll change that, get rid of the divided by 3, hit enter, close the calculator, and now you can see our arbitrary force is now in newtons because there's a 1-to-1 relationship. So our force sensor is reading our forces in newtons. So this leads us to the idea that we can measure forces. We're going to measure forces by using this force sensor, and that forces can be doubled and tripled and so on down the line. We can measure forces, we could arbitrarily measure forces by using things like springs and rubber bands. But once we get that set up, we can then use other instruments like the spring scale here or like the force sensor here. The force sensor obviously is much more precise. We can now get multiples or fractions of our rubber band units. Okay, well that's going to finish up investigation 1. I'll go ahead and process this video and I'll get set up and we'll be doing investigation 2 I'll be doing investigation 2 and have that up for you momentarily.